Aspect ratio. Okay. Yeah, aspect ratios. That's yeah. Cool. So, good morning, everyone. Am I audible? Okay. Whole be Yanida. So I think whole is small, so I think we don't need to. So previous two speakers, Professor Samanda and Professor Dilip, spoken related but different topics. I would say different era. One is very old quantum, and now Professor Dilip just finished covering the recent and the not so recent topics in quantum mechanics, and in particular many body systems. Okay, so I have title. I don't know, when Professor Nimai asked me what is the title, I was thinking what are the peoples are talking about. So I said quantum statistical mechanics, of course, in line with the celebration of this IYQ. I'm not going not too much technical, but rather I would just give a formalism of what quantum statistical mechanics is. Okay, but I will start with classical. Okay, and okay, here is a brief outline of what I would like to discuss with you all today. So I'll start with some story about bosons reaching reaches century. Okay, then historical developments of quantum mechanics. In brief, this would be a brief summary of all these early 1900 till recent Higgs. Okay, and then here is very brief on what is statistical mechanics and what is quantum stat mech, and some. It is also important to know what people are, what nations are doing, as say our government or the missions like National Quantum Mission. Okay, so I will cover a little bit of this also. Okay, I hope this will be a new variety to what you have been listening. So anyway, so let's see. So this is a small story that appeared in Nature Physics last year, July. So the title is Bosons Reach a Century. This is a story, so where it says that this quantum theory started in 1900, okay, with the Max Planck, as we all know, trying to explain the black body radiation. That was a big challenge during that time, but now we know. See, Bose, S.N. Bose or Satyendranath Bose appeared around 1924. He was, as per the story, he was delivering a lecture in Dhaka University, then suddenly appeared to his mind that such an statistical mechanics can also be done. Okay, and then he wrote this paper that contains a formulation of Planck's law that Professor Samanda was showing, because I'm not showing that equation here. And these was completely independent of classical mechanics or classical interpretation. Okay, so earlier where people were trying to extend the classical mechanics formalism to quantum, to accommodate quantum this observation or new observations during that time, but he was having a very independent, which is not related to this formalism, and he was not successful publishing his papers at the time during this circle in Asia and around. That's what the story says. Then later he sent to Einstein. Okay, so Einstein immediately recognized, and he even extended. First thing, he's translated the paper, published it in this journal Physics. That's a very famous, and it appeared in 1924. So that's where all these things appear. So Einstein in fact extended the work of Bose and even predicted this Bose-Einstein condensation can happen from this statistics. Okay, so that was a story of this beginning of this S.N. Bose here, and then it appears that for quite some time, the story of bosons or the study of bosons has been not in the limelight, because it is dominated by the studies of fermionic systems. See here, what do we mean by fermionic systems here? Okay, I will come to the later. Say for example, metals, they are all electrons, mostly electronic systems or metals or whatever. They are basically electron systems. so which are fermions. So there is also statistics to describe that. That's called Fermi-Dirac statistics. Okay. Okay, and okay, I'll just, okay. So these in the recent and the not so recent, there is a renewed interest in this, in the study of these bosonic systems. Of course, the quantum statistical mechanics formalism covers entirely all these quantum systems, which will show these phase transitions. Okay, so now one of the another thing that renewed our interest is laser. Professor Dilip was saying, right? Laser. So it was based on the Einstein's calculation of the spontaneous emission of coherent light. That is possible that he showed with this. He showed that, and then the very recent thing is this quantum computing. Okay, and this for this quantum computings, it is said that using boson has advantages over fermions for this particular quantum computing application. So experts are here, so they will explain in detail. I am not expert in this field, so I am just highlighting why there is a renewed interest in these bosons. Okay, so and many of the topics like this entanglement, I think the next speakers will cover that part. Okay, those concepts are very relevant for this modern quantum technology. Okay, these are based on quantum phenomena. Okay, so that is why this I think it was last year that they celebrated the 100th year of this bosons, or this appearance of this paper of Bose, and they declared, and that's what we are celebrating in this year, the International Year of Quantum Science and Technology. Now let's go. I'll just go through this quickly. There's all quantum era. See, the quantum continuation. So it all started with this Max Planck in 1900. Okay, then Albert Einstein's 1905. Of course, he had many papers, and one of the papers is regarding this photoelectric effect. That show that he assumed the quantization of energy also there. That sort of, he himself was not so positive about the quantum theory, but he was a main contribution in conceptual and many other respect. And the Louis de Broglie also appeared, and also Heisenberg. So up to 1925 we generally refer to as all quantum theory. Okay, so this was more or less semi-classical approximations. Okay, and the main tool was the Sommerfeld quantization rule that used. So it just improved from the Bohr quantization rule. Okay, and it was never a complete or self-consistent theory. Okay, then came these people here, Schrödinger, Dirac, Heisenberg. Okay, Heisenberg also appeared here. This time he was developing this matrix mechanics. Okay, that is very useful form of mechanics to describe the quantum systems. Now we have around 1935 with this Schrödinger cat, this concept came up. Then we have this in 1935 EPR paradox. I think yesterday Professor Rosen spoke about this. And then 1948 this Richard Feynman appeared, okay, in the picture. Of course, the Nobel Prize date, year I have written here. So most of them all got Nobel Prize. Huh? So now in 1952 we have this. In 57 there's another thing came up, so-called many world interpretation of quantum mechanics. Okay. Then in 1960s we have this first laser built. Then 1964 we have Bell, I think. Oh, sorry, I missed it. So it was Bell's theorem, the Professor Brosen's topic. Sorry. I hope somebody is speaking EPR paradox or not. I am not sure. Okay. Then in the very recently in 2012 this Higgs boson. Okay, and it was observed, and then Peter Higgs was awarded the Nobel Prize in Physics in 2013. Okay, so this is a very brief sort of recap of what people have been speaking over the last 2 days. And what is the difference in this modern quantum mechanics is, you could say modern quantum mechanics is entirely new mathematical formalism, and it's sort of very different. Okay, and it can very accurately predict many quantum phenomena, wide range of quantum phenomena. Okay. Okay, having said that, let's move on. So what is a statistical mechanics? Okay, so Professor Dilip just finished saying about phase transitions. So in order to have phase transition, we are not talking about one or two or few particles. Okay, so these are bulk systems. Okay, so statistical mechanics is a formalism that explains, or that aim to explain, the physical properties of matter in bulk, okay, on the basis of dynamical behavior. So in old times, the thermodynamic, as we all know, is a very old subject. Okay, it was empirical science for a long time, but people were not able to connect what is happening at the microscopic level to the macroscopic level, that we all can do experiment and observe. And this statistical mechanics formalism, or this theory, connects this microscopic world and the macroscopic world. Okay, so and this formalism allows us to study systems in equilibrium as well as in non-equilibrium. Okay, and what do we mean by bulk or macroscopic system? We are talking of number of particles of the order of Avogadro number. As Professor Dilip put it just a few minutes back, volume as well as the number of particles tends to infinity, but their ratio is finite, meaning the densities, if we count the number of molecules in this room, we cannot count it. This is finitely, countably infinite. Okay, but the density of gas molecules in this room is finite. That's the case. That's what we are talking about. Now, another thing is, with the increase in the number of particles, as say more and more number of particles, the energy levels, the separation of energy levels also becomes narrow and narrow. Okay, there's, in other words, you can imagine it to be sort of continuous band of energy. Okay, so what is the scope of this statistical mechanics formalism? Okay, so almost as unlimited as the range of natural phenomena. So we spoke about magnetic systems just a while ago. We spoke about liquid phase transition. We spoke about this phase transition quantum system as well. Okay, so you see, I just wrote down a couple of topics here. So it can even also explain biological systems. Okay, this is called soft matter systems. Okay, so there, so you see, statistical mechanics is a general formalism which applies to a system having large numbers of degrees of freedom, or you can say large number of particles, how they collectively behave. Okay, like this. Okay, now this is a very brief about the classical statistical mechanics. So I am just going the formalism, not much. Okay, so see, the entire description of classical statistical mechanics is a probabilistic description. So when we have that many number of particles, we cannot talk about equation of motion of one single particle or couple of particles. We have like 10 to the power 23 number of particles, and if imagine writing 10 to the power 23 number of equations, that's not possible. So we have to adopt another means, that is probabilistic description of the system. And what is the relevant question here? So for example, we have a large number of system or large number of particles here. Then we can ask, say at a given temperature, for example, okay, or at a given energy. So you can ask, what is the probability that this system can be found at a particular state, right? So that is one of the relevant questions that we ask all the time. Okay, so that probability, so there are a lot of stories behind this. Okay, and one of the person who actually I did not put name here, is the Boltzmann. Okay, he actually related the entropy with the so-called microstates. So that part I'm skipping here because that will be too lengthy here. So I'm just focusing now to that question. Okay, so it turns out that, of course, it depends on the system. There's a kinds of systems so-called microcanonical, canonical, and the grand canonical. So microcanonical is a system where you don't you have a fixed number of particle and a finite volume, which is not changing, as well as the fixed energy. They're all constant. In this case, the question that we asked, what is the probability that a particle can be found at a particular state, okay, is constant. So it's the same, all the states which are compatible or which is compatible with the given macro state, meaning defined energy, their probability of finding, they are all same. So at any point you pick one particle, they are equally likely to be in one of the state. Okay, but if we move on to other canonical systems, so-called canonical, this is like you have fixed number of particles, finite volume, but you allow energy to exchange between a system and the surroundings. This is a typical system, thermodynamic system. We have a system which is in contact with the surrounding. Okay, so there's we allow exchange of energy between the system and surrounding. Okay, and in that case, the probability that we just asked turns out to be this e to the minus beta ei. That's what we also heard a few minutes back. See, this is the expression here. The ei refers to the energy of a particular state. Okay, I refers to different state. Okay, so e to the minus beta, this is also called Boltzmann factor. So this Boltzmann factor or weight gives the probability. So the probability is an exponentially decaying function, and what this z at the denominator is the normalizing factor, and this is what is called as the partition function. This is the sum over all the states of this Boltzmann weight or Boltzmann factor. Okay, so you see, our question, of course, there are lots of arguments as to how we arrived at this relation, but assuming that we all accept that it is true, okay, and that's what it is, that's the probability that a system being found at a particular state depends on the energy, like this on the exponentially like this. Okay, yes. Oh, sorry, beta is 1 over kBt, is a thermal energy, inverse thermal energy. Okay, for everyone, sir. Is it always 1 by kBt, or is there any other cases? Beta is just 1 by kBt, just a constant. Okay, I should have put, but just to reduce the number of, beta is just a constant, 1 over kBt. Okay, so it's a compact notation. Beta is 1 over kBt. Kb is the Boltzmann constant. So kBt together is the thermal energy. So it's a ratio of two energies. So you're comparing energy of a system with respect to thermal energy. So it's always a competition. Okay, so whether the system interaction dominates or the thermal energy dominates. So it's a balance somewhere. Now that is the case. Now in a grand canonical, this is very in a thermodynamic system we have this system which also allows to have exchange of particle with the surrounding. That system is a grand canonical. In that case, the same question, what is the probability that a system is being found at energy state Es and the number of particle state defined as Nr. That is also kind of Boltzmann factor, but we have additional term alpha Nr, which is alpha is again chemical potential divided by kBt. Okay, and you see that Boltzmann factor is modified. So we have, or also we have to account for the energy change due to the exchange of energy. Okay, so see how this is how the probability expression is modified slightly, but overall the structure is same, and the Q is generally referred to as grand partition function. Okay, just for a grand canonical. Otherwise, we usually use just partition function, but to keep in mind what kind of system we are dealing about. Okay, now I have not written this famous equation of Boltzmann, which is written in his tomb also, k log omega, because I want to focus a little bit more on this partition function, because they are all related only, but that would be too detailed. Now, why partition function is important? See, initially I start out with probability question, but eventually for various calculations, what is necessary is just to find this z only, this partition function, because of the following reason. You see, once we know this partition function, this is for the canonical expression for the canonical, we can immediately write down the free energy of the system. And then you see this internal energy, of course this is for a fluid system, internal energy, entropy, pressure, these are all first order derivative of this free energy expression. And also I have a set of equation here, specific heat, then isothermal compressibility. These are very well known quantities that one can measure. But what is the difference between these two rows? You see, first row is the first order derivative of free energy, second row second order derivative of free energy, and we just talked about first order phase transition and the continuous or second order phase transition. In first order phase transition, what happens is, in one of these quantities will diverge at that particular control parameter points, like it can be temperature or it can be others, pressure, depending on the system. Okay, and if the phase transition is such that in one of this quantity, which is second order derivative of the free energy, is diverging, then those are generally referred to as second order second order phase transition. Okay, this is, if I am not wrong, convention adopted by Gibbs, I guess. Gibbs, he formulated in this way. Okay, but otherwise this second order phase transition we now call it as continuous phase transition. Okay, you see, pressure df by dv at t. Now for fluids, magnetic system also is the same, except for some other changes in, like say, instead of pressure we have magnetization, we have internal energy, entropy, they are same, specific heat, then isothermal susceptibility for solid or magnetic systems that we talked about in paramagnetic to ferromagnetic transitions. Okay, so you see, in terms of general formalism, they are all same, except for the difference in the quantity. Okay, for one set of parameters first order derivative, another set of parameters they are second order derivative. Okay, so this is a very nice I would say representation of what can be calculated out of this partition function. Okay, now let's move on to quantum state mech. Okay, I could have kept this at the end also, but I just put it here so that we already have an idea about what can be done. Now, in moving to quantum state mech, we all know classical mechanics is state is defined in this coordinate and the momenta in phase space QP. Now, it is to be defined in this wave function psi rather than this point in phase space. How do we change from that QP formalism to this wave function formalism? Of course, the Dirac notation, I just use Dirac notation. Now, the thing is, say in quantum mechanics, okay, sorry, I'll go back a little bit and explain one important concept. We are talking about equilibrium systems. In equilibrium, there is something called ergodic hypothesis. Okay, so for a system in equilibrium, this hypothesis has to be, or loosely, or it is has to be followed. It simply says that for a physical quantity, you measure it over a long period of time and average it. Okay, say at regular intervals of time, I just measure some quantity x, and those different quantities I average it at the end of my this long time measurement. I get a average quantity. And then now, in another situation, I have a system and I can make mental copies, like infinite number of copies. Okay, this is what, or this is the way in which we make it up to thermodynamic limit, going system into infinite, okay, regime, okay. And then you have copies of the same system, the same quantity. Now you measure at a single time frame, okay. At a particular time, I look at all these different systems and measure the quantity, and you average it. So this is called ensemble average, and the one previous is time average. So time average and the ensemble average should or will give you same value, and if this is followed, then this called the system is in truly equilibrium system, okay. If it is not followed, like in Glasses system, ergodic is not followed, ergodicity is not followed there, okay. Now let us go here, this quantum ensemble description here, okay. So I have this expectation value of this operator x cap. So x is some operator related to some observable, okay. In quantum mechanics, any observable is related to some operator, some Hermitian operator, okay. So so I have taken some wave function psi, and this superscript k simply refers to some particular copies. I just said about many copies, right, of the system. So you see this, and you average it over all these copies. You see, this is the ensemble average. You know, I just translate from classical way of writing to quantum way of writing. That's it, okay. But the concept remains the same. It's just a change of language. Of course, it's not exactly the same. If you go into there are technical differences at the end, but in terms of formalism, there are many similarities here, okay, except for the change in the language here. Now, having defined a wave function, we go always choose some basis to work with, and if we write something like this and put it back here, the expression of expectation value of some parameter looks like this, okay. But this line may not be so important, but I would like to highlight this one, okay. This is called density matrix that describes the ensemble, meaning this is giving the probability that we talked about in the previous earlier in this classical case, okay. So okay, so this is the amplitude of that function here, and now this density matrix is again can be obtained from this density matrix operator, or then simply density operator rho here, and the average quantity can now be written as this, okay. So now this rho here is the equivalent of our probability, that classical here, this one, okay. That's what I have written here. The probability that a state selected at random from the ensemble will be found in some phi n state, okay. So you see the concept is same. We still use the concept of this ensemble, many copies, okay. Assign some wave function or the state to work with, okay. Sorry, you see, this is the classical way of writing for that expectation value, average value. So this rho here is the density in the phase space, classical phase space, density of points, okay, and this is x is a quantity, and this is average. This is the standard average expression. Yes. This one?
No, the ensemble average. Yeah, this one.
Yes.
Here the wave function psi, it represents a step of the ensemble, not of the individual copies.
Sorry, it represents
A state of the ensemble, whole ensemble, not a state of the copy.
this for a copy. You can change. It's the same wave function, but for different copies. Oh, sorry. Now, I just put a comparison for this mostly for students, but anyway, just what the message is that they all look equation looks very similar, okay, but that the language has to be moved from classical to quantum, okay. Now, the implications of this is straightforward. We can study many thermodynamical systems like phase transition in thermodynamical systems, okay. Say for example, how do we study phase transition? Say for example in liquids, first thing is we have to write down equation of state, okay, that immediately can be obtained from this, for example, okay. So you see, the main idea that I would like to emphasize in this is just what is the formula, how to start. Okay, what Professor Dilip was saying is this is beyond the, all of this is done and that is the expression that you get. Okay, but before there is like a gap. This talk is like a gap. Just fill in the gap. What Professor skipped that part. Okay. So after we have to after we gone through this, we have to write down equation of state for this particular system. Then only we will start studying the system for different parameters like changing temperature, changing pressure, changing volume, how the system behaves. But to arrive at this something useful or some relevant equation like equation of state, we have to rely on this for systems consisting of many particles. Okay, this is the way it is done. Okay, but before statistical mechanics came about, these thermodynamical descriptions are all empirical. They do experiment, they get some result and try to formulate some relation, and that relation, of course, I'm not saying it's wrong, but it's sort of lacking the detail, or people did not know what was happening at the atomic scale. Okay, and this statistical mechanics fill that gap. Okay, that is the idea. And as I said at the beginning, the application of this formalism is very wide. Okay, very wide. Okay, and and the interesting, one of the interesting thing is this Fermi-Dirac. Okay, so depending for quantum stat mech, depending on the type of particles, either it's fermionic or bosonic, there are two statistics. Okay, Fermi-Dirac statistics and the Bose-Einstein statistics. Okay, so say for example in the stars, and this is shortly after, there's a story, this shortly after Fermi this or Dirac this statistics came, Chandrasekhar immediately applied to the study of stars. That's how he arrived at this Chandrasekhar limit. Okay, so the point is that this is applied to even stars and astronomical objects. Okay, and that is all inside the stars we have these electrons like fermionic system. So that's how he applied this Fermi-Dirac statistics. I have not shown the statistics here, equations, and for Bose-Einstein statistics like this Bose-Einstein condensation, they are bosonic systems. So what statistics is followed is this Bose-Einstein statistics. Okay, now, okay. So now moving away from the technicalities, I would like to highlight a little bit on very different thing. So let's see what are the quantum initiatives worldwide. This is very recent data. Country wise, you see India has invested about $735 million related to quantum, while China invested about 15 billion. Okay. Now let's look at just big countries. US, where is it? US is not. Where is US? Why? Oh, okay, 7.7 billion. So China has invested twice the amount of US. UK, although small, is about 4.3 billion US dollar, and figure is in billion dollars. Okay. Of course, there are others. So I'm just highlighting only the big players. See how China's. I mean, this highlights the China's ambition. Okay, we are not lagging behind, but in terms of dollars, it's quite a difference. Okay, but anyway, the point is many countries in the world are putting a lot of effort, in this quantum technology race. Okay, and now this brings us to a short discussion away from this technicality, and would like to highlight about what are the initiatives that the government has taken. Okay, now in this regard, I would like to mention something called this PM STIG, Prime Minister Science Technology Innovation Advisory Council. In 2019, they identified these 9 missions. Okay, say NLT, natural language translation. Then one of them is quantum frontier. Okay, then other is AI, national biodiversity, electric vehicles, bioscience for human health, waste to wealth, deep ocean exploration, and last is Agni. Okay, so these you see. So people have been mentioning the national supercomputing mission. That's another thing, and we have this quantum frontier. Okay. This is related to machine language, this AI, machine language translation, those things, AI related stuff here. These in fact are related actually. Okay, they have objectives are different, but the technique or the technique will be the same only. Okay. Now, what is this quantum frontier? Okay, I just put this Sundar Pichai in that Google's that quantum computer, this image. So here the objective is to control quantum mechanical system. Okay, you see the point is control a quantum mechanical system with large number of degrees of freedom. Here we are not talking about 1 or 2 atoms. Okay, with large number of degrees of freedom, many atoms. So this requires a very good knowledge of quantum state mechanics. Okay, and of course, consequently the applications. Okay, this is to build, as they say, an excellence in quantum frontier, as well as it's important for national security. Okay, security. Say in other developmental areas also, their planning is quantum computers, quantum chemistry, quantum communication, new material design, quantum sensor, and quantum cryptography. Okay. All right. So this is one thing, and another very relevant I just want to highlight is this national quantum mission. So national quantum mission is part of that quantum frontier. Okay. So it's a flagship program. The total budget is about 6,000 crores, and the duration is for 8 years, starting 2003 until 2031. Okay. So the objective you see is to have this quantum communication network to develop. Okay. Then quantum computing power, then magnetometry and atomic clock. Quantum material design, this is another aspect. Okay, and recently they have these thematic hubs they have designed. Okay, so these are hubs that will mostly be responsible for this. Say one of the hub is in ISC, which is for quantum computing. They will be dedicated to this, and at IIT Madras we have this quantum communication. They are the main player. And there is a quantum sensing and meteorology at IIT Bombay, and another at IIT Delhi. They will be looking after this quantum material and devices. Okay, they are not the one who are not going to work alone, but they are the hubs. In that hub, the other institutes like NITs and other institutes or university, they will affiliate. They will work together. Okay, this is called hub spoke spike model. It's a very recent model. Okay, of working. But you see, and the national level also people are working and promoting this quantum, and the government is very serious about it. And I think this understanding of this quantum state mechanics is also very relevant. Okay. Yes. Spike delay. Spike se propose tawdeng hoje NRF on badagi hoje proposal me amla ebako. Another model the ngasai individual centric project sing je phanam handharagana. So I know hub spoke spike model the hub na chok chok or kan moi the connector kan dane. Koi gi cooperative oina tawbage collaboration mode ta tawbage maina yam bole on thoreba. And see yam chawbo project ne quantum mission ja. Likewise sai gi supercomputing mission ju tawdone aduna swai the spoke ti lekte hoje hai baje say quantum computing na IISc the moi hub oidana. Ada moi gi reason to the leiba anakpada leiba NITs IITs oibe yai any moi jega collaboration tawdoine. Sai mentor gi ta. So they will be acting like a mentor, and the others will be working together. Okay. So I think I will stop here, and I am stopping early, and I hope it is useful. I did not go very technical. Okay. If you have any question, I would be happy to answer. Yes. Sigizra. Kashum kaide. See, just for writing purpose, I've just written the Helmholtz free energy. These quantities are all defined for Gibbs free energy also. Gibbs for the system for grand canonical system where you are allowed to have exchange a change of volume also. Okay. Kashum kaide. Oza habiro. Yeah, ayu khangde kharaga khangma khara haji.
I was listening to a talk by professor, reputed professor. He was giving a talk on quantum statistics, particularly Bose-Einstein statistics. And he told that the derivation of the Bose, SN Bose, on Planck black body radiation, it gives clue to the Bose-Einstein statistics, and somehow the derivation of the Planck, there may be a mistake. By chance, it is there. But I was not happy with that statement, and I objected to the person. Before I tell my objection, you please answer your question.
Oh, I know. I don't know about this argument, this mistake.
But because the same formula, both of them got. And if anyone why the same formula they can achieve, anybody can give some clue. So I answered like this from the audience. I raised my hand and I told like that. Okay, SN Bose derived the same formula, taking the statistics, assuming the statistics for what is called statistics for integral speed.
Yes, bosons.
Okay, and then they got it. Somehow, what Planck assumed is the harmonic oscillator quantization. Finally, harmonic oscillator is also boson.
Yes, yes.
Finally, it is just like an elephant. You touch the head, you touch the leg. Okay. It is the same body because harmonic oscillator. He assumed the harmonic oscillator and quantization. That is also bosonic things. So in that way, Planck is not wrong.
Yeah.
I answer like this, but I don't know my answer is correct or not. You think about this one.
Yeah, that's the same way. That the easiest classroom example of bosons is this phonons. This. So anyway, I think we can. If there's no question, then I will stop here.
If there is no question, comment, let us thank Lenin. Yes, Lenin. Okay. Okay, thank you.
Thank you.